This $40 silo of ordinary sand can heat your entire home through the coldest winter for pennies a day. It holds temperatures above 500 degrees for weeks with almost zero loss, something no lithium battery on Earth can do. Yet despite sand being the cheapest, most abundant material on the planet, almost nobody in America has been told it could replace their propane tank entirely. It's called a sand battery. By the end, you'll know what it is, how it works, and how to build your own. Let's dive in. Right now, if you heat your home with propane, you already know what winter really costs. The U.S. Energy Information Administration's 2024 Winter Fuels Outlook projects the average propane-heated household will spend between $2,000 and $3,000 on heat this season alone. That figure has climbed roughly 40% since 2019. Every October, you call the propane company. You schedule your first fill. You watch that truck back down your driveway and pump 400 gallons into a tank you probably do not even own. In most states, residential propane tanks are leased from the supplier. You are renting the privilege of buying their fuel at whatever price they set that week. Spot propane prices swung between $1.40 and $2.70 per gallon across 2023, according to EIA weekly data. You have zero control over which end of that range your next fill lands on. Then you fill again in December, maybe again in February if January was brutal. Each delivery runs somewhere between $800 and $1,200 at current national averages. And here is what no propane distributor will put on the invoice. You are not paying for heat. You are paying for a combustion reaction that converts stored chemical energy into warmth at roughly 80 to 85% efficiency in a well-maintained forced air furnace. That means 15 to 20 cents of every dollar literally goes up the flue as exhaust gas. An older unit running at 78% wastes even more. Over a 20-year span in a cold climate state like Minnesota, Vermont, or northern Michigan, a propane-dependent household will hand the supply chain somewhere between $40,000 and $60,000. At the end of those 2 decades, you own nothing. No equipment equity, no stored energy, no infrastructure, just a pile of receipts and a rented tank rusting in the side yard. Natural gas is cheaper per therm, but it welds you to a utility pipeline and a rate schedule you did not write. Air source heat pumps deliver impressive efficiency in moderate cold, but most standard models lose 30 to 60% of their rated capacity below 5 degrees Fahrenheit, according to a 2022 field study published by the Cold Climate Housing Research Center at the University of Alaska Fairbanks. That means the pump struggles hardest exactly when your heating load peaks. And when you see what a sand battery costs to build compared to a single propane fill, and what it costs to run per month compared to your current bill, you will understand why no propane company and no utility is rushing to tell you about it. The core principle behind a sand battery is so simple, it almost feels like it should not work this well. Sand is what engineers call a thermal mass. It absorbs heat energy, holds it within its granular, crystalline structure, and releases it slowly over extended periods. You already understand this if you have ever walked barefoot across a beach 2 hours after sunset and felt the warmth still radiating up through the soles of your feet. A sand battery takes that everyday phenomenon and scales it inside an engineered, heavily insulated container. You heat the sand using cheap electricity. That electricity can come from your own rooftop solar array, from a small wind turbine, or from off-peak grid power that many utilities sell for as little as 3 to 6 cents per kilowatt hour during overnight hours. In some deregulated markets in Texas and the Midwest, overnight wholesale rates occasionally drop below 2 cents. The sand absorbs that electrical energy through embedded resistance heating elements and converts it directly into stored thermal energy. Then it simply sits there, holding 500 degrees or more, waiting patiently for you to extract the heat whenever you need it. The property that makes sand so effective for this role is its specific heat capacity, combined with its tolerance for extreme temperatures. Sand stores approximately 830 joules of energy per kilogram per degree Celsius. Here is what that means in terms you can use. 1 metric ton of sand, heated to 500 degrees Celsius above ambient, holds roughly 115 kilowatt hours of usable thermal energy. That is enough to keep a well-insulated 1,500 square foot home warm for 3 to 4 days in US Climate Zone 6. Unlike a lithium-ion battery, which loses 2 to 3% of its rated capacity every single year through irreversible chemical degradation, sand does not degrade. You can heat it and cool it 50,000 times across decades, and it remains chemically and structurally identical. No dendrite formation, no thermal runaway risk, no cobalt, no lithium, no rare earth minerals, no battery management system watching for cell imbalance. Think of the insulated vessel like an enormous thermos flask. Instead of keeping coffee hot for 8 hours, it holds 500 degrees of thermal energy locked inside a steel silo for weeks. The insulation is where the real engineering lives. With 4 to 6 inches of high-quality rock wool or ceramic fiber blanket, thermal losses from a properly designed sand battery drop below 1% per day. That means if you charge it to 550 degrees on Monday morning, a week later, it still sits above 500 degrees. Now, if you are thinking this sounds too convenient, consider the comparison honestly. A Tesla Powerwall 2 costs roughly $11,500 installed. It stores 13.5 kilowatt hours of electricity. It degrades to 70% of capacity after 10 years, per Tesla's own warranty terms. And it does not even store heat. It stores electricity, which you then convert into heat through a resistance element or a heat pump, losing energy at every conversion step. Charging losses, inverter losses, resistance element losses. The total round-trip efficiency of that chain for producing room heat lands around 75 to 80%. A sand battery skips every one of those intermediate steps. It stores heat directly as heat. No inverter, no charge controller, no degrading lithium cells. The round-trip thermal efficiency of a well-insulated sand battery for space heating ranges between 92 and 98%. Almost every watt you put in comes back out as usable warmth. Now, if you are thinking that 500 degrees inside a steel drum in your basement sounds hazardous, engineers at the National Renewable Energy Laboratory in Golden, Colorado, addressed exactly that concern. Their 2021 technical report on thermal energy storage media confirmed that sand-based systems can be designed with entirely passive safety. The sand stays sealed inside the vessel at all times. Heat transfers out through a closed-loop air circuit or a liquid-to-air heat exchanger. You never open the container during operation. Hot air flows through embedded steel or ceramic pipes, pushed by a small fan or circulator pump, into your existing hydronic radiant floor, your baseboard loop, or a forced air duct system. The temperature your thermostat reads is whatever you set it to. The 500 degrees stays locked behind multiple inches of insulation. Using thermal mass for heating is not a modern innovation. Adobe walls in New Mexico have regulated indoor temperatures for centuries. Stone masonry fireplaces in Scandinavian farmhouses served the same function through Arctic winters. The Romans built an underfloor system called a hypocaust that circulated heated air beneath stone and sand beds more than 2,000 years ago. The modern, engineered version of this concept traces its industrial roots to concentrated solar power research in the late 1970s and early 1980s. The Solar One experimental tower near Barstow, California, came online in 1982 and demonstrated large-scale thermal energy storage using molten salt. Salt and sand share the same foundational physics. They absorb heat, hold it, and release it on demand. The key difference is cost and complexity. Molten salt demands corrosion-resistant nickel alloy piping, precise chemical composition management, and elaborate freeze protection to prevent the salt from solidifying in the pipes. Sand demands a steel container, insulation, and patience. A Finnish energy technology company named Polar Night Energy took this simplified principle and in 2022 built and commissioned the world's first commercial-scale sand battery, installed at the Vatajankoski power plant site in the town of Kankaanpää, Finland. The system was developed under the technical leadership of Markku Ilonen, a physicist from Tampere University and co-founder of Polar Night Energy. Engineers at VTT, Finland's Technical Research Center, participated in validation testing. Their published results confirm the system held temperatures at 500 degrees Celsius with minimal loss across multi-week storage intervals, operating through a full Finnish winter where outdoor temperatures regularly fell below -20 degrees Celsius. The Kankaanpää installation is not a pilot demo tucked behind a university fence. It is a working piece of energy infrastructure. Polar Night Energy's sand battery uses a steel silo approximately 4 meters in diameter, packed with roughly 100 metric tons of standard construction-grade sand. It stores up to 8 megawatt-hours of thermal energy. The local utility, Vaajajankoski Oy, charges the sand using surplus wind and solar electricity purchased during periods of oversupply, when spot market prices drop close to zero or even go negative on the Nord Pool exchange. When heating demand spikes in winter, the stored heat feeds into the town's district heating network, directly displacing natural gas combustion. Markku Ilonen stated in a 2023 presentation archived by the International Energy Agency that the installed cost per kilowatt-hour of thermal storage capacity in their commercial sand battery is roughly 1/10 the cost of equivalent lithium-ion storage. 1/10. That single ratio should make any homeowner writing a check for propane pause and reconsider the entire equation. And this is the part where the residential builder in you should start doing the math. A Canadian maker, electrochemist, and prolific technical publisher named Robert Murray Smith has documented the construction of small-scale sand batteries using steel drums, rock wool insulation, and nichrome resistance heating wire. His published builds, available on his YouTube channel and in printed technical booklets, demonstrate systems that store enough heat to warm a workshop or a small cabin for multiple days on a single charge. Total material cost in his documented builds ranges between $50 and $150, depending on drum volume and insulation grade. In Southern Africa, a non-profit organization called Solar Turbine Group International deployed community-scale thermal storage systems in Lesotho using locally sourced sand and fabricated steel containers. Those units provide cooking heat and space heating for rural off-grid health clinics. They have operated continuously for years with virtually zero maintenance because the storage medium has no moving parts, no chemicals to replenish, and no electronic controls to fail. And here is the claim that will send some of you straight to the search bar to check me. Polar Night Energy's published operational data from the Kankaanpää site shows their sand battery maintains usable output temperatures after 4 continuous weeks of storage with less than 7% total thermal loss. No residential lithium battery system, no vanadium redox flow battery, and no compressed air energy storage installation on the market today can match that duration to loss ratio for stored thermal energy at anywhere near that cost per kilowatt hour. The data is published. The site address is public record. Verify it yourself. If sand is cheap, non-toxic, fireproof, proven at commercial scale, and already heating Finnish towns through Arctic winters, the obvious question is why every propane-dependent home in rural America does not already have one. The answer is not physics. It is not safety. It is policy architecture. The Federal Investment Tax Credit, expanded and extended by the Inflation Reduction Act signed in August 2022, offers a 30% credit on qualifying residential clean energy installations. The word qualifying is doing the heavy lifting in that sentence. The statutory definition of eligible property under Internal Revenue Code Section 48 centers on systems that generate electricity from solar, wind, or geothermal sources. A sand battery generates no electricity. It stores heat. And heat storage, no matter how effective or how cheap, does not appear in the statutory language. The Desire database, maintained by the North Carolina Clean Energy Technology Center at NC State University, catalogs every state and federal incentive program for clean energy in the country. Search that database for residential thermal energy storage. The results are nearly empty. A few states offer modest rebates for solar thermal water heating panels with evacuated tube collectors. But a sand-based thermal battery that converts surplus electricity into long-duration stored heat for space heating sits in a regulatory void. It is not solar thermal because it uses no solar collector. It is not a battery under federal definitions because it does not store or discharge electricity. It is not a furnace because it burns nothing. It exists outside every category the incentive system was built to serve. The workforce structure reinforces this invisibility. The Solar Energy Industries Association's 2023 National Jobs Census counted roughly 350,000 workers in the U.S. solar industry. Those workers hold NABCEP certifications. They are trained, insured, and financially incentivized to sell photovoltaic panels paired with lithium battery packs. No NABCEP certification module for sand battery installation exists because no trade body has written one. No contractor can offer you a turnkey sand battery because no equipment manufacturer is packaging one for the American residential market. And the financial system completes the loop. Fannie Mae's Selling Guide, which dictates appraisal methodology for conforming mortgage underwriting, includes specific provisions for valuing residential solar photovoltaic systems as property improvements. It contains no provision of any kind for thermal energy storage. So, if you built a sand battery in your garage that cut your annual heating cost from $2,500 to $150, the mortgage market would assign that improvement a value of exactly zero. You would be saving thousands per year on a system the entire housing finance ecosystem treats as though it does not exist. Here is what you need to build a working, residential-scale sand battery. The primary vessel is a steel container rated for sustained temperatures above 600 degrees Fahrenheit. A standard 55-gallon open-head steel drum costs between $30 and $65 from industrial suppliers like Uline, Granger, or a local salvage yard. Critical rule: do not use galvanized drums. The zinc coating vaporizes at high temperatures and produces toxic fumes. Use bare, mild steel, or, if budget allows, stainless steel. Fill the drum with clean, thoroughly dry sand. Masonry sand from a quarry or concrete supply yard works best because its consistent grain size between 0.25 and 2 millimeters promotes even heat conduction. Play sand from a hardware store also works, but may contain more fines. Budget $25 to $40 for roughly 450 pounds of sand. Insulation is the component that separates a working thermal battery from an expensive hand warmer. Wrap the drum in a minimum of 4 inches of high-temperature rock wool blanket. 6 inches is better. Rock wool, rated for continuous service above 1,000 degrees Fahrenheit, is available from McMaster-Carr, Granger, or refractory specialty suppliers like A&H Refractories. Budget $50 to $80 for enough material to fully wrap and cap a single drum with 4-inch thickness. For the heating element, Nichrome 80 resistance wire is the industry standard. A coil rated for 1,200 to 1,500 watts costs $15 to $25 from DigiKey, Omega Engineering, or Amazon. The wire threads through the sand in a horizontal spiral at 3 to 4 vertical levels inside the drum. You connect it to a household 120-volt circuit through a PID temperature controller from a supplier like Inkbird or Auber Instruments, costing about $20, which automates charge cycle shutoff at your target temperature. For heat extraction, embed a 2-inch black iron pipe vertically in the center of the sand bed. Attach a small, high-temperature, brushless blower fan at the base, costing $15 to $30. The fan pushes room-temperature air up through the pipe, where it absorbs heat from the surrounding sand and exits at the top into a short duct run connected to your home's heating distribution. Total materials for a complete single drum system come to between $170 and $300 at current U.S. retail prices. Tools needed include a drill, a step bit or hole saw, wire strippers, high-temperature RTV silicone sealant, and a multimeter to verify connections. If you have ever wired a baseboard heater, replaced a dryer plug, or installed a thermostat, you have the electrical competence required. If you have not, hire a licensed electrician for the wiring portion only and handle the fabrication and assembly yourself. Robert Murray Smith's build guides include wiring schematics, part numbers, and measured performance data from actual operating units. What to avoid: Never load sand that has not been thoroughly dried. Residual moisture converts to steam at these temperatures and creates internal pressure that can rupture a sealed vessel. Always include a small pressure relief vent in the drum lid. Do not reduce insulation thickness below 4 inches to save money. Cutting from 4 inches to 2 roughly quadruples your daily thermal loss rate and turns a multi-day heater into a device that cools to ambient in under 18 hours. And do not use PVC pipe for the internal heat exchanger. PVC softens and releases chlorine gas well below 400 degrees. Use black iron, stainless steel, or ceramic. There are honest limits you should know before you start. First, a sand battery stores heat. It does not store electricity. If you need to power lights, a refrigerator, a well pump, or any device that runs on electrical current, a sand battery cannot serve that load. You still need photovoltaic panels, a generator, or grid connection for electrical needs. Sand handles thermal loads: space heating, domestic hot water preheating, greenhouse heating, livestock waterer heating, and radiant floor systems. Second, charging rate depends on your electricity source. If you charge solely from solar panels, your charge window is constrained by panel output and daily sunlight hours. In northern latitudes during deep winter, that may be as few as 3 to 4 hours of meaningful solar generation per day. Off-peak grid electricity fills this gap at 3 to 6 cents per kilowatt hour in many utility service territories. But you need to be enrolled in a time-of-use rate plan to capture those savings. Third, a single 55-gallon drum is a starter and supplemental system. To heat an entire home through a sustained cold snap in climate zone 5 or 6, you need roughly 2 to 4 metric tons of sand in a well-insulated enclosure. That translates to a footprint of approximately 4 feet by 4 feet by 6 feet tall. It fits in a garage corner, a basement utility room, or an insulated outbuilding. But it requires a concrete slab or reinforced floor capable of bearing 4,000 to 8,000 pounds. So here is the math one final time, stated as plainly as possible. Propane heat costs you $2,000 to $3,000 per winter, every winter, with no end in sight and no asset to show for it. Over 20 years, that is $40,000 to $60,000 gone. A sand battery system sized for whole home heating, built with 2 to 4 tons of sand in an insulated steel enclosure, costs under $1,000 in materials. Charged with off-peak electricity at 4 cents per kilowatt hour, it delivers equivalent thermal output for roughly $8 to $15 per month. Over the same 20-year span, your all-in cost, including the build, periodic insulation replacement every 8 to 10 years, and all the electricity to charge it, comes to under $5,000. That is a lifetime savings of $35,000 or more, and the sand never wears out. Researchers at the National Renewable Energy Laboratory tested silica sand through repeated thermal cycling to 600 degrees Celsius and documented 0 measurable degradation in heat storage capacity. The sand you load into your system this month could still be storing heat 50 years from now. If you want to power, heat, and cool your home off-grid, the Passive House files show you how. Full plans, exact materials, and the honest numbers nobody else gives you. It's not too late to start lowering your bill. Scan the QR code and see for yourself. So here is my question for you. If you had the budget and the space for one system this winter, would you build a sand battery for thermal storage, or would you invest that same money into more lithium battery capacity for electrical loads? Drop your answer in the comments because I genuinely want to know how you are prioritizing heat versus electricity in your setup. If this information was useful to you, subscribing and sharing is the single best way to help this channel keep uncovering the technologies that the mainstream incentive structure was never designed to recognize. Next time, we are looking at a solid-state device invented in 1821 that turns waste heat directly into usable electricity with no turbine, no moving parts, and no noise. That one is going to change how you think about every hot surface in your home.